Okay, the recording is running. There's something that I wanted to share with you, and it already takes up one page of my notes. This is a little clipping from the front page of the New York Times, the 14th of November, 1963, where two basic problems of math were solved. Imagine that on the front page of the New York Times. And that was about the continuum hypothesis and the axiom of choice. Paul Cohen had announced his solution. He had shown that CH was not provable. He had also shown that the axiom of choice was not provable. He did it by forcing, and it was important enough to appear on the front of the New York Times. When I looked at the archive of the New York Times, apparently they archived a later edition of that day because it wasn't on the front page anymore. But I did manage to get the text, and I'll put it on the ELO later so you can read what the New York Times had to say about the solution of two basic problems of math. Also interesting, that was the time that set theory was being introduced in secondary schools. And as you can see, the proof involves set theory now used in schools. I doubt if the kids in the schools would have understood the forcing business, but never mind. So what is my plan for today? Well, my plan for today is to revisit Cohen's proof once more and write down all the details, show how to generalize it in a few directions. But first, I need to finish some business from last week, because we haven't really shown yet how the extension, we haven't really shown yet that the extension M of G we haven't done this yet. But before I do that, I just want to recapitulate what we have done in the last few weeks so that we are all sort of on the same page, so to speak. We started with a proof uses only finitely many axioms. Right? Because a formal proof is just a finite list of formulas where you obey the rules, and at the end is your statement. So it suffices. That was the first sort of insight that we had to construct an interpretation of the language of set theory. Well, these are the important bits of the language of set theory: the element of relation and the equality relation, and of course the and, or, and whatnot. But those are not; those don't need interpretations of themselves. They will get relative interpretations, such that satisfies well. It satisfies phi1 up to phi k, but not phi. The phi that we want to show is unprovable. And so, we've been working towards phi being not CH, or rather phi being CH. And we've been working towards finding an interpretation that satisfies phi1 up to phi k and the negation of the CH. And you can put many set theoretic statements here that you like. There is a very famous one. Suslin's hypothesis. I may come back to that next week because it's a pretty result, it's a pretty question, and the way to prove its disprovability is quite pretty too. So I may do that next week. By the way, if anybody has a favorite set theoretic statement that they want to try, that they know is unprovable and they want to show, they want to see how it could be unprovable, let me know. Maybe I'll be able to work it into next week's lecture. Anyway, that is how we started out. And then we found out via, shall we say, reflection and the Löwenheim-Skolem theorem, we were looking, in the beginning, we were looking just for structures that would satisfy phi1 up to phi k. We were going to worry about phi later. And what we discovered, using the reflection, we could find a V beta that would satisfy phi1 up to phi k. And then the Löwenheim-Skolem theorem, and also and the Mostovsky collapsing result, we found a countable transitive M that satisfies that was the work that we did in the first forcing lecture when we were doing absoluteness and such. And of course, for convenience, and I mentioned this too, we simply, some people might say lazily, assume M satisfies all of Z of C. Formally, we cannot do that, but we can pretend that we do it. And then later, when we look at our proof of non-provability, we say, but oh, wait, our proof of non-provability used only 10 times as many actions as we were looking at in our phi1 up to phi k. So let's do the countable transitive model that satisfies all those 10K instances of actions, and that is good enough. So you can always go trace back through your proof and say, well, I only use those actions, and then go through our previous thing using only those. But in the end, once you know how that is done, you simply say, well, assume all of Z of C and don't be bothered really with the particular instances that we use. Okay, and the countability of M the countability of the M's allows us to make extensions of such models in a very systematic way. And that is what we have seen the last few weeks. First, I started out with the negation of the continuum hypothesis, we saw more or less how you can add omega to many new subsets of omega so that you destroy the continuum hypothesis. Well, you needed to do it with care, but we saw how that care could be formalized. And what was the care? Well, a partial order. In M, and now we're getting to the general systematic way. What we did before was use finite partial functions to create those Aleph too many subsets of omega. But now we're going to take stock and say, well, what are we actually doing? We take some partial order in M. G, an M generic filter. On P, and what the hell was that? Well, we knew what filter meant, or we knew what filter meant. We defined what filter means, but it looks very much like what Cohen defined in the 30s for filter to be. Oh, and our partial order had a maximum. The maximum we called 1. And if it doesn't have a maximum, we simply add an extra point and say you are going to be the maximum of the partial order. There are some that don't have an official maximum, and then we just stick some element at the top of the thing. Generic generic got the following definition. We take an arbitrary dense set in the partial, for every dense subset of the partial order that happens to be a member of M, we want G to intersect that dense set. And of course, dense means every element has something below it that sits in the dense set. Okay. The countability of M, they gave us such G's exist. In fact, every P and P is a member of one of these things. And of course, it sits in many G because if it sits above a Q and Q sits in the G, then it sits in the G itself. So there will be many such filters. By the way, when you read books, you will see, or papers on forcing, you will see all kinds of terms seemingly contradictory that describe the same thing. Some people don't call the filter M generic on P, they call it P generic in M. Means the same thing, but they want to stress the partial order more than the model, I guess. But they will mean the same thing. Right? Useful things incompatibility of elements is an important phenomenon because it happens lots of times, and incompatibility means just what I'm writing down here. Incompatibility means that P and Q, think about it for a moment, can never be in the same generic filter G, because then part of the definition says there should be something below you. And so compatible means that yes, P and Q can sometimes be in the same filter. Not necessarily so, but they could be. Useful to know. And anti-chain, that is also a useful thing to have, as we will see today. We call a set A an anti-chain if P if all elements of the set are mutually incompatible. It means that a filter can pick only one point, maybe none, but it can pick only one point from each anti-chain. Zorn's lemma. Oops. Zorn's lemma says maximal antichains exist. And of course, we're using choice anyway, so yes, maximal antichains exist. And this shows us that G is M generic. G is a filter and intersects every maximal antichain. And since the antichains are maximal, and it's a filter, it intersects every maximal antichain in just one point. That's I think I put it as an exercise in homework last week or in group interaction, but the idea is that if D is dense and you take a maximal antichain inside D, then it is automatically maximal in P. And if you take a maximal antichain, then everything that sits below a member of that maximal antichain is dense. So D is dense. So that is a thing that you need to use. And if A is a maximal antichain, then D consists of all the Q's if you look at everything that sits below a member of the antichain, then if it's maximal, then you get a dense set. And you use the maximality a lot in that case. Anyway, those are all kinds of things that we need to know about partial orders if we want to do our forcing in an efficient way. And you have seen all these things in action in the homework and in the group interaction bit already. The maximal antichains are very useful in building nice, sort of very economic names for things in the extension, as you have seen, again, in the homework, for example. We have defined what it means to be a p-name, and the definition was recursive. It's a relation. All its first coordinates are names, and all its second coordinates are members of P. And this is a sound definition by induction on the epsilon relation, or something slightly stronger than the epsilon relation, which is well founded, and you can make the definition work. Or you can look at the homework of last week and say, hey, we can repeat the construction of the universe, but then construct a universe of names, and you get the same thing. And finally, then, we see what the members of M of G are going to be. We take all the names, we evaluate them according to this recipe, and that will be our extension. And last week was devoted to this, truth in MG truth in MG versus what we can say in M. That was the theme of last week. How can we describe things going on in M of G using only what we have available in M? And we defined this interaction okay, and I'm going to use the short version of the evaluation business, because I don't want to write this val all the time. So we were just hanging the G on the tau. If we take the formula phi, put the evaluations of the names tau in the places of the free variables, and then relativize to m of g, if that holds for every g that contains p, then we will say that p forces that formula. And if you want to do this in LaTeX, you need this thing from the AMS fonts collection. Anyway, that's how it's done in LaTeX. Notice a person in M, in as much as there are persons in M, cannot do anything with this definition. It's just we. We want to say, well, if we look at all the generic filters that contain P and all the time the same formula is true, well, then it must be default of P that's going to happen. And we are saying P forces it. Fine. That is our way of looking at things. But we would like to be able to decide this forcing business without looking at G's. One note, if the poset is not really trivial, I mean, a linearly ordered set has a generic filter, the whole partial order. Think about that for a moment, but it's not very exciting. But for example, if below every element you can find two incompatible things, as in our poset of functions, if we have a finite function, we can extend it two ways so that the two extensions don't get to be combined into a function anymore. If P is non-trivial, then no G is in M. No generic filter is in M, the reason being that you can calculate that the complement of a generic filter is dense if the partial order has this property over here. Well, if it's dense and G doesn't intersect it, then apparently P minus G is not a member of M, and so G is not a member of M. This was the hard work last week. We defined we also define this. You can define this simply in V and then later relativize to M. That's why I put using only stuff from M in brackets. We can take a partial order in our universe V. We can write down all the formulas that we did last week. And then later say, but wait a minute, we are working in a model M. We have a partial order in there. We can relativize the whole thing to M. And that is what we did when we formulated a few of the theorems anyway. We defined this using only names and P and the notion of density. That was it. And we did it in steps. The big one was doing the equality, and the rest was derived from this. And the relativation to m came when we were doing the existential quantifier. When we say there exists, we can play that game in our universe and get a nice formula, forces star, but we can relativize forces star to m, and then every one of those existential quantifiers will have to be relativized to m. Lovely. Let's see how far we are. What then? Okay, we did that. So how did that help? Well, the main technical result is this. If P is a member of G, and the forcing relation P forces phi tau 1 up to tau k holds in M, so the relativized version holds in M, then we have what we want. We stick the values, the G values of our names in the formula, and we relativize the whole affair to M of G, and we find that that holds. This is part of that. This is one arrow in that definition here, except that we don't have the forcing thing. We have the forcing with the star. Well, it's one way. If P is in, if we have this, and P is in G, then we get this. Okay, that's one thing. And the other thing is going the other way. If it so happens that a relativized version of the formula phi in M of G holds, then there is a P in the filter that forces it in M with the star. Now, I did this last week, and I was making a bit of a hash of it because it turned out that my notes were a bit garbled. So I wrote it down, and I want to give you at least the salient bits. And I think what is it? And I did it for the equality, and I'll give the things where I went wrong. I'll do those again. So what did it mean for P to force with a star that two things were equal? Well, it meant two things. That's a whole mouthful, but I had to write it down. So if you take, what do you need? How do you prove that? How do you prove? How do you force that tau1 is equal to tau2? When you want to decide it completely inside of M, then you have to look at all kinds of subsets of P and see whether they're dense in various areas given by P. And I've written down this dense set. The dense set depends on pi1, on S, and on P. Those are the things that it depends on. It also, it doesn't depend on pi2. The pi2 comes as a, in the quantifier. And by symmetry, the same thing happens if you go the other way. If you take a pair that is in tau2, you can write down another dense set where you interchange the 1 and the 2, and that has to be dense below P as well. And so if we assume that this happens in M, then we need to relativize everything in M as well. Well, what happens? Take X in tau 1g. What we want to show is that X belongs to tau 2g. Because we want to show that tau 1g and tau 2g are the same. Well, X is pi 1g there is a pair in tau 1 such that X is the interpretation of the first coordinate of that. Okay. Let's see. And of course, the S1 comes from G. Pi is X is equal to pi 1G. Well, pi 1G is there because the S2 has to be a member of G. So we take a member of G that sits below pi 1, below P, and S1, then still R forces tau 1 is equal to tau 2. And there is a Q below R in that set. Okay, then Q is less or equal than R, less or equal than S1. Now look at what D1, D pi 1, S1, P or R wants us to do. Well, Q is below S1, hence we find something in tau 2 with we find this. All right. Okay. Q is less or equal than S2. Let's see. Oh, I'm sorry. We find Q in D1 as R intersected G, because the thing is dense below R and R is in the filter. So one member of that thing has to be in the filter. So S1, S2 is in G. So pi1, sorry, pi2G is a member of tau2G. And Q forces pi1 is equal to pi2. Okay, but induction, I mentioned this last week, everything is by induction on the rank, if you will, of the names. Q forces pi1 is equal to pi2, forces with a star. Q belongs to G, induction we've started with a member of tau1G and we showed that it's a member of tau2G. And the symmetric density will tell us that tau2G is a subset of tau1G, and there we have it. But the important thing is this inductive business over here. We prove the whole thing by induction on, say, the rank of the name. Okay, well, it's 2:45. What shall we do? I'll leave the other bit for the second hour. It's nice to have a break. Right now, we'll continue at exactly 3 o'clock, and I'll pause the recording now. And let's get this show on the road, shall we? So, what's the other thing we need to show? Well, let's do this in black. If tau1G and tau2G come out the same set, then we want a P in G that forces it with the star. How do we get this P? Well, we look at a dense set. Well, actually, we don't look at, we look for a dense set. And the question is, well, what is it going to be? Well, it's going to consist of 3 pieces. It's going to consist of all the R is going to consist of all the R's that force tau1 to be equal to tau-G. We want G to intersect this. We want it to intersect it, but it's highly unlikely that this set is dense. Because not every condition forces that tau1 is equal to tau-G. There might be members of P that have a completely different opinion about this. So we could have another type of points, those are the points R with the property what? There is something in tau 1, and R will be convinced that pi 1 is never ever going to be a member of tau 2. And how does R do that? Well, R should be convinced of the fact that pi 1 is going to be a member of tau 1. And the easiest way to do that is by having R below S1. And now we get a whole mouthful. R doesn't want pi 1 to be equal to any one of the pi 2s that could potentially be a member of tau 2. So what do we want? We want for every pi 2 S2 in tau, for every Q in P, if Q is very sure if Q is really, really sure that pi 1 is going to be a member of tau 2, then we want Q to be incompatible with R. So R really, really doesn't want to have anything to do with members of the partial order that try to convince him that something from tau 1, that pi 1 is actually a member of tau 1, tau 2. And of course, we can also have people who really don't want tau 2 to be a subset of tau 1, and they will give a symmetric set. Now, so let's call this D equal or something like that. We want two things. We want to show that this union is dense, and we want to show that G intersect DI and G intersect DII is empty. Because if this union of the three things is dense and G doesn't intersect two of them, then it has to intersect the third one, and we are in business. So those are the two things we have to show. We have to show that G doesn't intersect D1, and D2 will be by reasons of symmetry. Okay, so let's say that R is a member of G intersect DI. Then what's going to happen? We get a member of tau 1 that has its second coordinate above R. So we know that pi 1G is a member of tau 1G. Lovely. If we have a member of tau 2g, then it is of the form pi 2g with pi 2 comma s2 in tau 2 and s2 in g. If pi 1g were a member of tau 2g, then it would be one of those x's, and we would get this. And if this happens, then we can use the inductive hypothesis again. Pi 1 and pi 2 are lower in order, in rank, than tau 1 and tau 2. Then we find a member P of G that forces the two things to be equal. Okay, but now take Q in G and Q below P R S2. And then also, of course, S1, because S1 sits above R. Yes, but Q is below S2 and Q is compatible with R. Last week we wrote Q and R are parallel because they're in the same generic filter. But wait a minute. We have a Q, we have a pi 2 S2, we have a Q which is below S2 and it is compatible with R. That means that looky here, Q satisfies this, Q satisfies this, and does not satisfy this. That means that it cannot satisfy this either. On the other hand, it sits below P, so it should also force that pi 1 is equal to pi 2, and that is a contradiction. And the same thing goes with DII, that goes simply the other way around. Okay, so why is the union dense? Well, take a P that we want to show that the union of those three things is dense. Where was it? Where was the set? I lost my set. Oh, here it is. We wanted to show that this union was dense. Well, if P happens to be in the D sub equal sign, fine. we don't need to look any further. So if it's not there, then we're going to find something below it that is in that's either in DI or in DII. And we take the bit that I didn't symmetrize. So we're going to assume that this fails. That is what I meant below 1 fails. This thing is not dense below, for some pi, this is not dense below p. So that means we get well, what does it mean that it's not dense below P? We get an R less or equal than P such that no Q below R is in no Q below R is in that particular set. Well, if it's not in that particular set, that means that for every Q less or equal than R, we get the following. What does it mean to be in that particular, what does it mean to be in that particular set? Look closely. If you are below S1, then there must be something going on. Well, we have A implies B, but we have not A implies B, and we know that that means if an implication doesn't hold, it means that the antecedent holds and the consequent does not. So we get a negation sign in front of this thing over here. Okay, let's see what that means. And I've written it down. It means that for every Q below R, well, Q, it means that the implication fails. It means that Q is less or equal than S. So in particular, R is less or equal than S1 simply because every Q below less or equal than R is less or equal than S1, in particular R. But for every pi1, every pi2 S2, something goes wrong. So what happens now if then we must conclude that Q is incompatible with R, because if we had a Q with this property that was compatible with R, we could find an S below it, and then because S is below Q, it means that it is less or equal than S2, and it means that it forces equality. And also, because S is below R, it also satisfies the negation of that conjunction. And there is our contradiction. And the important bit is that apparently R is a member of DI. So if P does not force tau 1 is equal to tau 2, and it is because of the failure of the first condition, then we can find an R below P that is in DI. Therefore, the union of those three is dense. And there we are. Okay, and this is the correct way. This is how I should have done it last week. And in practice, we use this. We defined the forcing bit using all the generic filters and whatnot. This is purely a definition using formulas and everything. And we have, what we get in practice is that these two are now equivalent. And the other thing that we use is that if we discover that something happens in M of G, then that is because it is being forced by, no, wait a minute, I'm going to do the official bit. If it's true, it's actually being forced by an element of the filter. And so one is the definability. We can simply use the forcing relation to define stuff inside M, where we have to keep in mind that even though we write it forces, we should formally be writing forcing with a star, but we are lazy and we don't. And two is the truth lemma that says if something happens, it is being forced. And that is what we've been using a few times already. Okay, ZFC. Why does ZFC hold in MLG? Okay, now I go back to my notes of last week, and you can go back to those as well, because I think I scanned them already. Well, M of G was transitive, so we already got a few things for free. Um, Simply because M of G is transitive, we know that it satisfies extensionality and regularity, or foundation, if you will. Pairing, union. Well, you actually did that in the group interaction or in the homework. Easy names. Infinity. We had a name for omega, so done. Power set. Again, that was homework or group interaction, relatively easy name. You can write down, not too difficult. You basically take the power set of the name of your set and do a little bit with it, and that will be a name for the power set of the interpretation. Choice. How do we get choice? Well, take a name. And the nice thing is we use choice in M to prove choice in MG. Because basically what we do is we take an enumeration of the domain of sigma. All those pi's that are the first coordinate of a member of sigma, we use AC in M to do that. And tau will be this name. Now look very closely. We take all names for ordered pairs gamma comma pi gamma. And then, of course, that's simply a set of names, and we multiply it by singleton 1. And then that's a name, that's a p name for something. Well, it's a p name for a function. Tau g is simply tau g is a set of ordered pairs that is a function that enumerates a set, and there you have it. Oops, I'm sorry. We have defined a function whose range, we have defined a function with domain and ordinal whose range contains sigma g. And now you can use easy tricks to put a well order on sigma g. That's it. separation. Okay. What does separation look like? Well, we have a formula and we want to separate the things that satisfy the formula from what? Well, from a set. And so how do we do that? I have to be careful. We want, what do we want? We want this. So we interpret the taus, and I'll put the taus together into one thing that says writing. We interpret the taus, we interpret the sigma, stick them in the formula, and we want to separate all the members from sigma g that satisfies this formula. And we need to find a name for this. But the forcing relation is definable, so we can use it. We take rho to be all the pairs pi comma p, and they come from the domain of sigma. And p respectively, and p forces what? Well, pi is a member of sigma, and like I said, I abbreviate the tau 1 up to tau k with just a single tau. And this is what we can write down. We can write it down by the definability lemma. And now, when you do the calculations, then I think I'll stick this in the group interaction later, because it's a nice exercise in working with names again. It's also on my notes, and if you look at my notes, you can crypt the result from there. But actually, this, like I said, some of these things are nicer to do yourself, so you can actually get an idea of how you work with the names. All that. And it uses the truth lemma once or twice too. And the same goes for replacement. But the way we do it is, some might say, by cheating a little bit. Because we have separation, and so we can replacement can be done as follows. If we know that see if I have all the things there. I'm not sure, but yep. Then this is what the replacement axiom says in one form or another. If you know that you have a sort of a functional relationship between okay, I think yeah, I think the A should go in there, but that's not really important. If you have a functional formula, then for every set, there is another set such that for everything in the first set, the image is in the second set. And you could ask for B being exactly the range of that function, so to speak. But all we need is a big set that contains the range. And that is what we'll be doing. So we have the formula given names. We want to find another name. Where are we? We want a name rho in M of P such that what? That's an error. Here we go. That satisfies the formula with the, and of course, everything relativized to M of G, but okay, let's put it, let's do that. So where do we, how do we get this? Well, we go back to M. We simply use the reflection like we did a few times. This is how we did the reflection business. We can find a beta in our hierarchy of V's that contains all the things that we need. If there is a name that does the thing that we want it to do, then there is already a name in V beta. And that's it. Notice every member of R is a name. So if I multiply R by singleton 1, I get a name again. And this name works. Again, you can check it by taking the evaluation of R or rho and get that every member of rho of G, sorry, every member of sigma G has its image in rho of G. Okay. Now, what is there left to do? Well, I want to go back to not CH. And sort of do the whole thing once more. And the important thing is I want to calculate the new value of continuum. One thing that I didn't mention, but I should, Cohen started with a model that satisfied the generalized continuum hypothesis. He had to start with something, and the only thing that was sort of given at the time was Gödel's constructible universe. That everybody calls L these days, and that is from around 1940. And why did Gödel construct that model? Well, in L, we have the generalized continuum hypothesis and the axiom of choice. So Gödel provided us with a model of set theory that actually satisfied the axiom of choice and also the generalized continuum hypothesis. And that was the only model that was available at the time. So that's what Cohen had to start from. And so he had a little bit more than we just said, let's take a structure that satisfies the axioms. We don't know what continuum is. But if we follow Cohen, we know what continuum is. It's simply L of 1. And we know 2 to the L of 1 is L of 2, and 2 to the L of 2 is L of 3, and so on. And we can use that in some of our calculations. And our partial order that was those finite partial functions that we used 2 weeks ago already. What did we do? Well, G, generic, gave us a function from omega 2 cross omega to 2, and it gave us F alpha being the natural number such that F was injective. F was an injective function from omega 2 of M into the new power set of omega. And you probably still remember what the dense sets were that were needed to guarantee this. The next thing I did, I will now do in a bit more generality. General lemma Why do I do it? Because I need it in the further properties of this model. In studying the further properties of this model, actually I proved this lemma already, but I'm just recycling the proof to get a more general statement. If x and y are members of n, and g is a function from y to m in m of g, okay, then there is a function in M with domain X and codomain the countable subsets of Y, such that this happens. And some people express it like this. Okay. So if you have a map, you have a function from two old sets, so to speak, two sets from X, from M. You have a function that goes from X to Y, and like I said, the two sets, the domain and the codomain, belong to M. Then you can approximate that function somehow using a multi-valued function from X to Y, but the multi-valued function is not very wild. It has countable values only. So you know your G up to countably many points. You sort of say, okay, G runs through Y, and I have it under control at least a little bit. Well, let's prove this, and then we'll have a break. Take gamma take a name for gamma and P and G such that P forces gamma is actually a map from X to Y, or from X hat to Y hat. In M, define let's do it in the old-fashioned way, but later we'll do it maybe a little bit nicer. We fix a member of Y, and here is what we do. If Q is in P and it is below P, then it should force the value y on x for gamma. And if it's incompatible with p, we make it point to a constant function, the function with constant value y0. And now, okay, we have seen that using this, we actually get, if we calculate r, if we calculate the image of g under this particular relation, then we get our function g back, and we always get a function for if we interpret this. That's because p forces it to be a function. How do we define f of x? Well, we've done this before. From this relation, we define a set-valued function. F of x are all the possible y's such that for some q, x and y together with q are in the relation. And we use the axiom of choice a lot because we choose a function that associates to every y a qy with that particular property. And if y is not equal to z, then qy and qz are incompatible because we are forced to be a function. And if r is less or equal than qy and less or equal than qz, then r will force that y and z will be the same thing, which they are not. And so the set of qy's is an antichain, and so if y goes to qy is an injective map, and we know, I'm not going to prove that again using the delta system lemma, antichains are countable. And there we have it. F is countable valued, and that is what we wanted to establish. Okay, that's a good time for a break because we're going to reap some consequences of this, but we'll do that after the break. So at 4:05, we'll continue. But I need to pause the recording. So where were we? Okay, we have done this this technical lemma about the Cohen partial order. You can capture every map in the extension by a map with countable values in the ground model, as we call it. So how does that help us? Well, for one thing, if you have an ordinal in M, and that's the same as being an ordinal in M of G, we have seen that the ordinals are the same, then we don't lose any cardinals when we go from M to M of G. We don't gain any cardinals either. That we don't gain any cardinals is relatively easy. If alpha is a cardinal in M of G and beta is less than alpha, then no map if alpha is a cardinal in M of G, then no map in M of G that goes from beta to alpha is surjective. Hence, no map. And we had an exercise a few weeks ago about downward absoluteness and upward. Being a cardinal is downward absolute. But if we want to go from left to right, okay, alpha is a cardinal. All the natural numbers will stay natural numbers because they're absolute. Omega is omega and it stays a cardinal. So we can start with an ordinal that's bigger than omega and say, well, what happens if that is a cardinal in M? Well, if beta is less than alpha and then we have a countable pipe that captures our F. And okay, we use that countable pipe, but then the range of F is a subset of the union of all the values of big F. And what is the cardinality of the union And alpha is a cardinal that's uncountable. So it's bigger than L of 0, and it's also bigger than the cardinality of beta itself. So F is not on 2. And there you have it. Alpha stays a cardinal. Cardinals are preserved when we move from M to M of G. Lovely. Exercise, and I put this in the homework. You can prove a little bit more. All the cofinalities are preserved too if you move from M to M of G. And there is a connection between the two. If all cofinalities are preserved, then all cardinalities are preserved. The converse is not true. You can make an extension where all the cardinals stay cardinals, but some lose their cofinality. But that is a little bit more difficult than the things we have done so far. What did we not do yet? Let's calculate. We didn't do that yet. I think we had an estimate last week, but now that we know that the ground model satisfies GCH, we can be quite precise. We already have that 2 to the L of 0 is at least L of 2, because all the cardinals have been preserved. So we can write L of 2 without danger of confusion. L of 2 in M and L of 2 in M of G are the same thing. So we don't use the M and the MG anymore. Well, the other thing that we're going to show is that 2 to the L of 0 is less or equal than L of 2. And how do we do that? Well, take a subset of omega. So assume we have a name and its evaluation happens to be a subset of omega. Okay, we take our P we take a P that forces that tau actually is a subset of omega. And just like in the case with the maps, but now let's make names rather than relations. We need to turn this into a name, and we want it to be the name of a subset everywhere. So why not say that it's just singleton 0 if we are incompatible with P. If Q is not in the ultrafilter G, then it doesn't really matter what we do. So the empty function, which is the maximum of our partial order, will force that tau prime is a subset of omega, and P will force that tau prime is equal to tau. So if you calculate the tau value, the G value of tau and tau prime, then you get the same thing. Some of this, again, I leave as a homework or as group interaction work. So all subsets of omega come from names that look pretty nice, like so. they are quite simple. They have as the first coordinate already members of omega, so to speak, and as second coordinates members of P. We can make them even nicer. Take a map. We take a map that goes from n to the power set of P, and AN is a maximal antichain in the Q's such that n check n comma q is a member of tau prime. And we make an even simpler name. We forget about most of tau prime, but we keep only the second coordinates that are in the maximal antichains. And then again, of course, it's still a name of a subset of omega. And now, it's still a name that gives us the same subset as tau. You can calculate this using the generic filter. The generic filter picks something out of AN or not. It could miss, it need not intersect AN because AN is not maximal in P necessarily. If AN is maximal in P, then it means that N is certainly an element of tau. But it need not be. We only take maximal antichain in the things that force N to be a member of tau. Okay. So what did we do? Well, every subset of omega has a, well, what shall we say, very nice name. This is sort of a minimal name. You cannot, if you leave out any one element of the name tau prime, you're going to change it in some generic ultrafilter. If you leave out one n check comma q, some ultrafilter is going to make a difference between tau prime and tau. So you really need the whole tau prime. It's a minimal type of name. How many of those very nice names are there? Well, how large is our poset? Our partial order is of cardinality L of 2. All those finite functions together, that gives us cardinality L of 2. And our names, tau prime, is basically a subset of omega cross P. It's omega, it's the domain of omega check cross P. Well, that has cardinality that still has cardinality L of 2. But tau prime is countable. Why? Well, it's countably many antichains. Every antichain is countable, so there you have it. So, at most, we have at most Aleph 2 to the Aleph 0, very nice names. But hey, GCH says, Aleph 0, Aleph 2 to the Aleph 0 is equal to Aleph 2. And we find that indeed okay, for once I put the M's and the MG's there just to make sure that we are unambiguous. How many subsets does omega have? Well, at most Aleph 2 of mg, which is the same as Aleph 2 of m. So we not only make CH false, we can actually give 2 to the Aleph 0 a specific value. Exercise. And nothing new is really needed. You also get, if you do this calculation with omega 1 of m instead of omega, then the only thing that really changes is that you do maximal antichains among conditions that force that alpha belongs to tau rather than n belongs to tau. And then how large are the names? Well, the names have cardinality at most Aleph 1. And so then we get Aleph 2 to the Aleph 1. Very nice names for subsets of omega 1, but that is also still Aleph 2. So the calculations are roughly basically the same, except you stick in Aleph 0, Aleph 1 instead of Aleph 0. And so what do we get? We also get that two sets of different cardinality can have the same number of subsets. Remember, when we started out with the cardinal arithmetic, we had all these weird conditions. What if the continuum function is constant for a while? And some people would think, well, can it ever be constant for a while? Answer, yes. Here we have a situation where the continuum function is constant. 2 to the Aleph 0 and 2 to the Aleph 1 are the same, and they're equal to Aleph 2. Okay. Let's see how much time we still have a bit of time. I want to insert one picture, and I hope that my editor doesn't act up. And I want to move it around just a little bit. Okay, here we go. That was fine. I picked this from an article by Robert Solvay from 1963. It appeared in 65. The title of the paper was I will put a copy of this paper on the ELO so you can read it for yourself. It's only one page. It's just an announcement of results. And he starts out with an M that satisfies V equal L, and that's the same thing that Cohen did. L is Gödel's constructible universe. And here is the theorem that I wanted to highlight. Take an infinite cardinal in M whose cofinality is uncountable. Then there is an excellent extension of that model where 2 to the L of 0 gets that particular value. Okay, what does excellent mean? Excellent means same ordinals. Well, that is what we know how to do with generic extensions and same cofinality function. And hence the same class of cardinals, as I mentioned a few moments ago. That's one theorem. The other theorem is you can do it for larger cardinals as well. Take an infinite cardinal, and that is regular. So the first cardinal is regular. It's equal to its own cofinality. But it's the other cardinal has larger cofinality, and then you can make 2 to the small cardinal equal to the bigger cardinal, and keep the continuum function what it was below that cardinal Aleph. I'll show you how to do that in a moment with Aleph 1 and Aleph 0. I'll indicate how to do that. I'll see if we have the time. And here is another theorem. Maybe we'll talk about it next time if you cannot find anything that I should prove consistent. You take a few Aleph i's. This all takes place below Aleph omega. These are Aleph n's that we're talking about. And what Solovay shows is that you can prescribe the value of 2 to the Aleph I for every I less or equal than k. So there is a lot of freedom in choosing the value of 2 to the kappa here and there. Okay, well, how about theorem 1? I need to create some light here, but okay, that's okay, fine. Well, theorem 1 is easy. If we use the language of Solovay, I would have put a kappa here, but okay, Solovay used an Aleph. Why not indulge him for a moment? Take this partial order, the finite partial functions with this domain, and run it through our proof. We get an injective map from Aleph into the power set of omega. So we get at least Aleph many subsets of omega. We get at most, because we can calculate using those nice names, how many new subsets of omega there will be constructed. And this partial order also has this property that anti-chains are countable. So no cardinals are lost and the cofinality function stays the same. That's something that you will find in the homework. Partial orders whose anti-chains are countable are very good for forcing because they don't destroy cardinals. They don't destroy cofinalities. And they get a special name. It's called the countable chain condition. Countable anti-chains means countable chain condition. I don't know why that happened, but anyway, that is what goes on in theorem 1 of Solovay. Now you can play with this a lot, and so but I want to look at theorem 2. So we take an infinite cardinal, but uncountable, and let's take L of 1. So let's be specific. Take L of 1 and some kappa bigger than L of 1 with the cofinality of kappa bigger than L of 1 as well. We want to make 2 to the L of 1 equal to kappa. And apparently we want 2 to the L of 0 to stay L of 1. That is what Solovay's theorem 2 says. We should be able to do that. Okay. Well, we start with M. It satisfies V is equal L. Well, if we don't know what it means, so we take the consequence GCH. And if you want to know what V equal L means, in Jech's book, there is a chapter on constructible sets. And there is also in Cohen's book a chapter on constructible sets, and you can learn there what V equal L is all about. Okay, so what do? Well, we go back to homework 12. Remember, in that homework, we talked about countable partial functions. And you had to show that there was an anti-chain of cardinality continuum, but you also had to show that there were no anti-chains of cardinality continuum plus. So in this case, anti-chain, so these are the countable, these are functions with countable domain. The domain is a subset of kappa cross omega 1. And of course, the values are 0 and 1. And if G is generic, and using this generic function, we can get kappa many subsets of omega 1. Nothing essentially changes in this case. And so we get a map from kappa into the power set of omega 1. Well, the mg power set of omega 1. Okay, but now we have the same problem. Do we lose any cardinals? Do we lose any cofinality? What is going on? Well, the same worries as previously when we did Cohen's model, we have now. But you also showed, like I just said, all anti-chains in P have cardinality at most L of 1. There is an anti-chain of cardinality continuum, but continuum is L of 1 in our ground model. We have GCH there. And there is no anti-chain of cardinality L of 2. That is what you showed. No anti-chain of cardinality 2 to the L of 0 plus. And 2 to the L of 0 plus here is L of 2. So all anti-chains are of that particular cardinality or smaller. But that means that U maps are captured by pipes that are L of 1 wide. In the Cohen partial order, we could capture a new map by something that was everywhere countable. Using the anti-chains, using exactly the same method as a few moments ago, we can now capture every map by a multi-valued map where all the values have cardinality L of 1 at most. And that's it. If alpha bigger than L of 1 is a cardinal in M, then it is still a cardinal in M of G. No change in the proof. If we have a map from a smaller beta to alpha, then the range of that map is captured in a set of cardinality beta times L of 1, which is less than alpha. End of story. We don't need to change anything to the proof, except we stick L of 1 in there instead of L of 0, and that's it. Okay, but what about L of 1? L of 1 is not so lucky, because if we do this trick with L of 1, nothing, yeah, we get a map, and from omega to L of 1 to omega 1, and it's captured by a set of size L of 1. Yeah, right, it's captured by L of 1. If L of 1 is collapsed, then we have a problem. Our extension is no longer excellent because we lost the cardinal. However, something new happens. Suppose we have a name we have a function from omega to a set in M, but G, of course, is in M of G. And G is gamma G, and we don't want to, without loss of generality, we just assume that we turn that into a name of a function from omega to X. And we're not going to do anything silly, we'll just assume this. All right. Take a Q in P. Well, Q forces, there is a Z. Q forces that the thing is a function, so, well, it forces that gamma 0 has a value. But then we look at the forcing about the existence and everything. So we can get a name for the element of X that is the value. But then we can go even further. We can find a member of X that is forced to be equal to this little sigma. And in short, S forces gamma 0 is X check. This has got nothing to do with the function. It just means if you point at an element of X, you can actually identify it with a specific element of X itself. Okay. Okay, we have 5 minutes, and in the 5 minutes we should be able to do this. So here we go. Take Q0 less or equal than Q and X0 in X such that Q0 forces that gamma of X0 is equal to gamma 0 is equal to X0. Check. Okay. Recursion. If we can do it for 0, we can do it for 1, we can do it for 2, we can do it for 3, we can do it for 4. This we can do, by the way, in every partial order. But what we cannot do in every partial order, but we can do it in this one. Remember, these are countable functions. And we have a sequence of functions that is increasing. Q is a function, Q0 is a function that extends Q. Q1 is a function that extends Q0, and so on. We can take then R is less or equal than Q, for sure, because we took a decreasing sequence. And this is still a member of the partial order. This wouldn't have worked in the partial order with the finite functions, because the finite functions would grow, their union would be a countably infinite function, and it wouldn't be a member of the partial order. But here, the partial functions were countable, so the union of these countable functions is still countably many countable functions, is still a countable function. And what does it do for us? For all n, okay, wait. For all n, R forces that gamma n is equal to x of n, check. Okay, take F to be this is a function from omega to x that belongs to m. And then R forces that gamma is equal to f. Okay? Okay, we're almost there, but I want to finish this so that you have something to think about. What did we show? D gamma consists of all the R's with the property. There is a function from omega to x, and R forces gamma is equal to that function. We have just shown that this is dense. You give me the name of a function and a condition in P, I will find a stronger condition that will end a function in the ground model, and the stronger condition says that new function, that's just this old function here. Okay, but take an R that belongs to our generic filter and sits in our dense set. It comes with an F. And then we find that our function G, here we have it. This function G, well, it's an old function. It belongs to M. Okay, but that tells us two things. One, every subset of omega comes from a function from omega to 2. And we have just shown every new function from omega to 2 is already an old function. And 2, omega 1 stays a cardinal. There is no new function from omega to omega 1, so there cannot be a new bijection between omega and omega 1. Omega 1 stays a cardinal. The power set of omega doesn't change. Oh, we have made sure that 2 to the L of 0 is equal to L of 1, and L of 1 is still a cardinal. And to show finally that 2 to the L of 1 is actually kappa, we do the same computations as in the previous hour. That's a few moments ago. The same computations. The cardinality of the anti-chains is now L of 1, so we have to do other powers, but the result is the same thing. Okay, I want to leave it at that. And so if you have a favorite consistency result that you want to see next week, let me know via email or whatever. And otherwise, I will certainly do something with Suslin's problem because I like the proof, and maybe something else about stationary sets. But we'll see what will become of that next week. Okay, let's stop the recording and